So again, welcome all of you, and thanks for coming. Let me share my desktop so I can talk about the plan today. Okay, the plan of the day is, as always, I'll start out with any questions you might have. And then after that, we'll get into just a review of what it means for two matrices to be similar to each other. We talked about that last time, but we're going to talk more, so I figured I should do a quick review, and it's easy. And then we'll talk about a theorem that says that similarity is an equivalence relationship. So we've talked about equivalence relationships a few weeks back when we decided that RREF was equivalence also. So I'll talk about similarity being an equivalence relationship. And then we'll talk about the trace of a matrix. I mentioned it before. You've had a homework problem on it, but now we're going to get more involved in the trace. Nice thing about the trace is it's easy, and it has some nice properties. Then we'll get into the properties of similar matrices. And then we're going to move into a big application, although it's more of a math application, but lots of other applications use it. And that is, and I love the word, diagonalizable. It just rolls off your tongue so well. So we'll talk about what does it mean for a matrix to be diagonalizable. And then we will make that a verb, and we'll diagonalize a matrix. And we'll talk about how can you diagonalize a matrix. And then we'll talk about, we'll look at eigenvalues again. And I guess again, that should be vectors, not values. So we'll look at eigenvectors, and we'll talk about when are eigenvectors linearly independent. So again, all the stuff we've done in the past is coming up again. And how does that relate to diagonalization? Then we'll get into the eigenspace for an eigenvalue. And again, these are definitions. If you don't know what they are yet, that's fine, but you will hopefully by the end of the hour and 45 minutes or so. And then finally, we'll talk about complex eigenvalues and eigenvectors. Remember, we find an eigenvalue by taking the determinant of A minus lambda I, which is a polynomial, and then we find the root of that polynomial. And hopefully you remember from basic math or basic algebra that roots of polynomials are not always real. So we can have complex roots, and if they're complex, how can you look at the eigenvalues and eigenvectors in a nice way? So that's the plan for the day. Hopefully it all works. And again, if I make errors, I'm not perfectly myself today. I'm doing my best, so doing my best. So hopefully, but please let me know if you see any mistakes or whatever, because today is a little different for me. Hopefully you'll understand. But at least statistically, by Wednesday, I should be completely done and better. That's the good news. So are there any questions you might have?
Yeah, could we go over 11? It's pretty basic, but I can't get a determinant that includes the one eigenvalue they gave within itself. So
Okay, so that's exercise 7.1.11.
Yeah.
Okay, so let me copy it out. Okay, so here's 7.1.11. And it says, find the eigenvalues and eigenvectors of the matrix. One eigenvalue is -3. Okay, so what you first have to do, if you want to find the eigenvalues, what do you have to do?
You have to find the determinant. Well, yeah, no, sorry. You have to multiply lambda by the identity matrix and subtract it from the matrix that you're trying to find the eigenvalues of.
Right, right. So we're gonna do that. So that's the first step. So hopefully you're down with that. And again, it's a little messy, but it's not that bad. So I'm making a matrix out of it, 3 by 3. Okay, so what we're going to do is on the diagonals, you're going to subtract lambda I. So you have 9 minus lambda I. Lambda. So subtract lambda, sorry. And then 2, and then 8, and then 2, and then negative 6 minus lambda. And then negative 2, and then negative 8, 2, negative 5 minus lambda. And what do we do with that matrix?
Find the determinant of it.
Yeah, we find the determinant. So far, so good? So now let's go find that determinant. It's a bit messy. So let me get there. Okay, so you're gonna have 9 minus lambda. And if there's any step that you're not understanding, please stop me and ask. And then you're gonna have times the determinant of its minor. And notice that 9 minus lambda is in the 1, 1 position. 1 plus 1 is 2. Negative 1 of the 2 is positive 1. So it stays positive 9 minus lambda. And then we have negative 6. Negative 6 minus lambda times negative 5 minus lambda. When you have these negatives multiplied, it all becomes positive. You okay with that?
Yeah.
So that's, in particular, I'm just going to write it as 6 plus lambda, just to make it a lot easier to write it out. Back to the math. 6 plus lambda, 5 plus lambda. Makes it a little simpler. Okay, and then we're going to have a minus 4 or plus 4. Any questions so far?
Nope.
Okay. Now, in this case, there's no zeros, so I'm just going to go by the first column, first row. It doesn't really matter. There's no easy one. Do you agree?
Yeah, it's not like 9. It's not easy to take the determinant of.
Yeah. So that means I'm going to have to do 3 of these. So now we're going to have 2. Now 2 is in the 2, 1 position. 2 plus 1 is 3. Negative 1 of the third is negative 1, right? So it's a minus 2. Are you okay with that? Okay. And now we're going to find the determinant of the minor when you get rid of the second row, first column. And we get 2 times negative 5 minus lambda. And I'm going to write that as negative 2 times 5 plus lambda. It's a little easier to type. Let me know if I'm skipping too many math steps. And then you're going to have a minus 16. Okay, and then you're going to have, notice the negative 8 is in the 3, 1 position. 3 plus 1 is 4. Negative 1 of the fourth is positive 1. So we just have the negative 8 or minus 8 times. And now let's find that determinant. We have 2 times negative 2 is negative 4. And then we have 8 times negative 6 minus lambda. Any questions so far? Okay, and again, there's a lot of, yeah. Huh?
Shouldn't it be positive 4? Negative 8 times positive 4 minus 8.
So we have the negative 8. And when you get rid of the third row and the first column and third row, we have a 2 times the negative 2. Right?
I thought you eliminated the first row and the third column to get the minor for 8.
No, I'm going about the first column.
Okay.
Yeah, I could have gone about the first row. And in the end, you
Oh,
get the
I
same
see.
answer.
Okay.
But I'm doing the column. So I'm see this -8 here. That's the one that I am using to find a minor. Do you see? So
Yeah,
I'm
now
going
I get
down, not across. And you can go across. And that's something I mentioned is it really doesn't matter as long as you're careful, because I don't think one's easier than the other. I didn't do the easier one, but I didn't do the harder one either. I think they're equivalent. Don't you agree?
Yeah.
If there's a 0, it's clear. You use a 0, but there's no 0 here. Okay, so let's clean. So let's go back, insert math. All right, so we have 9 minus lambda. And times. And now let's work this out. You get lambda squared. This is pretty messy. And then we're going to have plus 11 lambda. Because 6 and 5 is 11. And then we have a plus 30 plus 4 is plus 34. And then we have a plus, and now we have a lot of junk to work out. There's -2 and the other minuses, I can get rid of the minuses, make that a plus. So basically all these minuses go away in this middle term. And we get, let's see, so we get 4 lambda. And then we have a plus 20 plus 32, which is plus 52. If I did the arithmetic right. And again, let me know if I didn't, but I think that's good. And now let's do the next one. And here we have our lambda. We have a -8 times -8 times negative lambda is minus 64 lambda. And then we have a 32. And then ooh. Okay, so this one's messier. Let's do it this way. 8 times 6 is 48. 48 minus 4 is 44. 44 times 8 is the same as 11 times 32, which is 352. And that is so 352, it's a minus 352. Any questions on that messy part? Hopefully I did my arithmetic in my head right.
Yeah, it looks pretty similar to what I got. I'm still kind of confused because mine, when I checked the solutions to it, it didn't include -3, and
Now it's possible the book's wrong, but I didn't work this one out, but I am now. At this point, I think it's easier to pop this into Symbolab. Probably could have done it before, but I wanted to kind of at least show you how to do determinant. But I'm hoping that you don't need practice on how to FOIL, right?
yeah.
So I'm going to put this into Symbolab. I may have to turn the lambdas into X. And I'm not sure if you did the same thing.
I did, but then I just replaced the upper right. I just erased the upper right line of it to make it a lambda. So
Yeah, so I'm just going to drop it in Symbolab. Let's see. Oh, it did like the lambda. Interesting. See what it does. Did it multiply it out? Yeah, so it gives lambda, negative lambda cubed. I wonder if I can copy this. Let's see. So it gives negative lambda cubed minus 2 lambda squared plus 5 lambda plus 6. Let me put that in because you're not looking at that. So -1, -2, 5, and 6. Negative lambda cubed. And then that was -2 lambda squared. And then +5 lambda plus 6. Any questions so far?
Nope. Let me plug that into my calculator and see if that will spit out -3.
Yeah, actually, I could do this quickly in my head. You just plug in -3, see if you get 0. So -3 cubed is 27. And -3 cubed is 27. And then 9 times 2 is 18. So 27 minus 18 is, now we're talking about 9. 9 minus 15 plus 6 is 0. So the book is right. Any questions on that?
Nope.
So we can factor this. And like I said, I could factor this by hand. I don't want to. And these are the kind of things you're always allowed to use a computer for. I would never tell you you have to do this by hand, but I do expect you know how to do it by hand. So I'm just going to drop it in Symbolab. And I'm pretty impressed that Symbolab actually can handle lambda because I copied and paste. And you get negative lambda plus 1, lambda minus 2, lambda plus 3. Any questions on that? Plus 1, minus 2, plus 3. So let's do that. So it's negative lambda plus 1 lambda minus 2 lambda plus 3. Okay, any questions on that? Okay, now, by the way, the book is assuming we're doing this whole thing by hand. That's why they're giving us one of the eigenvalues. If I force you to do it by hand, how would you use the one eigenvalue as -3 in this work that we did? Anyone know? I just realized.
Would you divide it by lambda plus 3, polynomial long division?
Exactly. You do polynomial long division by lambda plus 3. And you'd end up with a solution. But actually, honestly, I wouldn't even use hardly their one eigenvalue is -3. I would use the rational root theorem and say, hey, the only possible roots, if they're nice and they're whole numbers, which they are, it turns out, are 1, -1, 2, -2, 3, -3, and 6, -6. So it's got to be one of those, and then I just figure out which 3 it is. And it turns out that lambda is -1, 2, and -3. So eigenvalues is -1, 2, and -3. Any questions on finding the eigenvalues? Okay. I don't know if I'll do all of them unless you really need me to. But let's do now an eigenvector. I'll let you choose. You want to do it for -1 or 2? Doesn't matter.
-1.
Okay. So what I would do, especially since I'm doing this on a computer, is I'd copy and paste this matrix. And now what I'm going to do is I'm going to take lambda and let it be -1. So if lambda is -1, 9 minus lambda is 10. Negative 6 minus lambda is negative 5. And negative 5 minus lambda is negative 4. Is that clear? Okay, notice that if we look at this, the first and second rows are not multiples of each other. Is that clear?
Yes.
Yeah.
So what that means is, what can I do with the third row immediately? Without even thinking, just using theory.
Make it
They're all
zero.
zeros.
Yep, I know that it becomes row of zeros because because the basis or the dimension or I guess the rank of this matrix is 2 or less, which means that when you RREF, the bottom row must all be zeros, and as long as you have 2 linearly independent rows, then you haven't changed anything in terms of the similarity, RREF similarity. Okay, then I'm gonna, just to make things easy, I'm going to switch the first and second rows, just so I don't have to deal with fractions. And actually, before I do that, I think I'm just going to zero out that 10. I'm going to multiply the second row by negative 5 and add it to the first row. So that makes that 10 a 0. And if I multiply negative 5 by negative 5, I get 25 plus 2 is 27. And if I multiply negative 2 by negative 5, I get 10 plus 8 is 18. Is that clear? Okay, now I can work more. You know how it always is. I'm going to do a few things at once, if that's okay. One thing I'm going to do is hit some enters. There we go. Okay, so I can divide the I could divide the first row by 9, make that 27 a 3, and the 18 a 2, and divide the second row by 2, sorry, make that 2 a 1, make the negative 5 a negative 5 halves, and the negative 2 a 1. Any questions so far? Okay, now I can take that matrix and let's do some more. So I'm just RREFing it. You could do it with Simple Lab too, but this one's not too bad, although there are some fractions. So now what I'm going to do is I'm going to take the third, I guess, the first row, multiply it by, let's see, 1/3 times 5 halves. So 5 6, and add it to the second. So that becomes a 0. Notice 2 times 5 6 is 10 6 or 5/3. And then 5/3 minus 1 is 2/3. Any questions on that? Okay, and then the last two things I'm going to do is I'm going to switch the first and second row. So we get a 1 on top, a 0 next, and a 2/3. That guy is a 0. And that's a 3. And I'm going to divide by 3. So that if I divide by 3, that becomes a 1. And the 2 becomes a 2/3, which is good, actually. Any questions on that? Okay, I'm looking for an eigenvector. See if you can give me an eigenvector that has no fractions. So what would the coordinates of that vector be?
-2, -2, 1.
Yeah, almost. -2, -2, 3. So the idea is you let the free variable that be 3 so that you can get rid of that 2/3. And then you get minus 2, 3. Okay, does that make sense? That's what they wanted, and then you do the other two. Do you need me to do the other two, or do you get the idea?
No, I get the idea now. I figured how to take the eigenvector, but I was getting very lost with the determinant. I tried doing it like 4 times by hand. I should have just used something like Symbolab or Desmos or something.
Yeah, it's messy. It's messy, and I you saw my last exam. Do I keep my promise on not making you do really horrible, messy stuff?
Yeah.
Yeah, and that's going to be true. I'm going to expect you. I mean, but I would not feel guilty giving this on the exam, allowing you to use Symbolab. Hopefully, you'd be okay with that. And of course, you wouldn't even do all of these steps, but I wanted to show you at least a couple of the steps. So yeah, you use a computer, you guys are going to get out of here and then get out of your bachelor's degree. You're going to get a job and you're going to use a computer, aren't you?
Presumably.
I hope so. Otherwise, you're never going to keep a good job. You need to know how to use a computer to do this kind of stuff. Okay. But if you don't understand the ideas, it doesn't help to be able to use a computer. Does that make sense? Other questions? If there aren't, we can move on. Okay, if there's no questions, let's move on. And we're kind of in the eigenvalues and eigenvectors. We're spending some time on them because they're really important. So we're continuing on doing a major use of them, which may not be obvious at the very beginning of today, but by the end, it should be pretty obvious that, yeah, this is a biggie. So let me remind you this happened on Friday. Do you remember? Yeah, Friday that was. Just double checking something good. This happened on Friday, and that was A is similar to B if A is equal to P inverse BP. Do you remember that? Okay, and A and B have to be square matrices, or you don't even talk about it. Is that clear so far? So we talked about I wrote down this definition on Friday, but I wanted to remind you because now I'm using it. So then comes the big theorem about that definition of similarity. Okay, so the theorem is that similarity is an equivalence relationship. Have you learned that word outside this class before? What it means for two things to be equivalent?
Like in any setting or just a math setting?
In math, yeah, definitely math. Okay, or heavy science, but yeah, basically math.
I think we've had it brought up in a few science classes before. I can't recall which one specifically, but it sounds familiar.
Yeah, because it's pretty pure math. It's pretty much pure math. Yeah, and I'm in a psychology class. I'm not even going to go there. they just would use it totally different. But this is a math term. So this is what it means. Okay, so for two things to be equivalent, you have to have three facts that are true. The first fact is that A must be equivalent to A. Okay. So otherwise, we just don't call it equivalent. Okay. The other is if A is equivalent to B, then B is equivalent to A. Does that sound reasonable that you'd want that? Okay, just as ideas even? Is that if this guy is equivalent to this other guy, then hey, the other guy is equivalent to this guy? Do you see how that works? Okay, so the first is called reflexivity, the second is called symmetry, and the third is called transitivity. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. Okay, And that makes sense. That's something you'd want. Do you agree? Okay. So by the way, equal sign is an equivalence relationship. Do y'all know that? If some number, if x is equivalent to, is equal to y, then y is equal to x. If x equals y, and you always know that x equals x. And if x equals y and y equals z, then x equals z. So you're used to seeing those, aren't you?
Yeah.
But it turns out that you don't have to have it equal to be equivalent. And that's important because with matrices, you don't have to have the matrices being equal for them to be equivalent. Okay. So I should prove this because I like proofs that are easy. Do you too? So here's the proof. All right. So I have 3 things to prove. This is really easy. How do you prove number 1? That A is equivalent to A?
I mean, I don't know. It
Because
just
A is A.
Yeah, it just is.
No, you have to show that A is equal to P inverse AP for some P. A is A doesn't work. Do you see? We actually have to use this definition. This is a definition of being equivalent. So why is A equivalent to A?
P inverse times P equals the identity matrix, and the identity matrix times A is equal to A.
You got to be careful. You cannot say BP equals PB because that's not true in our class, right? With matrices, you can't flip. Is that clear?
Yeah.
It's really easy if you know what to do, and if you don't, you'll just sit there, which I think a lot of you are just doing, right? Sitting there. And as soon as I say it, you'll like, oh yeah. So let's do it. Because we have to find a good P. So just oops. I hate when that happens. Let's try this again. Let P equal the identity. And will this work? Then what is the identity inverse? Oops, over here. That comma, there we go. What is the identity inverse times A times the identity? What's that equal to?
A.
Yeah, because that's the identity inverse. Let's just do it one at a time. A times the identity is A, right? But what's the inverse of the identity matrix?
I.
That's IA. But what's I times A?
A.
And I'm done. Do you see how that works? So I've proven that A is equal to a P inverse A times P. And I picked the easiest P I can imagine. Do y'all agree? Okay, let's do number 2. So let A be equivalent to B. Then by definition, and I can just copy and paste it, A equals P inverse BB for some B. Is that confusing or is that okay so far? Any questions on that? Just by definition? All right. Well, I want to show that B is equivalent to A. So I need B by itself. How can I get B by itself? What can I do?
You can left multiply by P.
Good. I can left multiply by P. So I can say PA is equal to P inverse B P, which is equal to what's P times P inverse?
I.
IBP. What's IB?
B.
B, P. Okay, so now I know that PA equals BP. So now what can I do? I need B by itself.
Right, multiply by P inverse.
Yep, right, multiply by P inverse. Then I get P inverse is equal to B P inverse. But BP P inverse is equal to B. I think I'll just do 2 steps at once if that's okay. All right. So now I now know that B equals PA P inverse. Why am I basically done? I just have to state something. Because we look at the definition, it's not quite exactly looking the same. Because I need to show that B is equal to an inverse of a matrix times A times the matrix. And why am I done? Any thoughts? The idea is I can just let the P be the inverse of our P. And P inverse is what? So what is P inverse?
P.
Just P.
That's P. We had that theorem a long time ago, that P, the inverse of the inverse is the original matrix. So now we can say that B is equal to a, where are we? There we go. It's equal to P inverse times A times P inverse. And now I got it written right. So I have now B is the inverse of a matrix times A times the matrix, where the matrix is P inverse. Anyone lost on that, on number 2? Any questions on that? Okay, let's do number 3. It wants it to be 4. Huh? There we go. Okay, well, we know that A is equivalent to B and B is equivalent to C. So since A is equivalent to B and B is equivalent to C, that means that A is equal to P inverse BP. Any questions so far? And we also know that B is equal to, it might be a different matrix. Remember, the letter P is not important. What's important is that it's a matrix. So let's call it Q inverse. CQ. Anyone lost on what I just wrote? Any questions on that? So now I just substitute. So I have A equals P inverse times this B, which is Q inverse CQ times P. So let's write that out. So A, is equal to, again, P inverse times B, which is Q inverse CQ times P inverse. Anyone lost there? Oh, sorry, times P, not times P inverse. All right, now I can use the associative property of matrices, matrix multiplication, and I can say that's P inverse times Q inverse times C times QP. Any questions on that? And remember how I can rewrite P inverse times Q inverse? We had a little theorem about inverse multiplication.
The inverse of P times Q.
Not quite, not quite. And this is why this is actually good that it's not that.
QP.
It switches. Remember that you switch the order of multiplication when you do an inverse. So it's actually going to be QP all inverse. Times C times QP. Do you remember that little rule of inverses? Okay. And why am I done?
Because it's just a matrix inverse times C times another matrix.
Times, except for the word another, times the matrix.
The matrix, yeah.
The matrix, not times another matrix, but times the matrix that had the inverse at the beginning. Okay, and that's it. That's the proof. Any questions in this theorem that the equivalence relationship, that this really is equivalent? Otherwise, you shouldn't use the word equivalent for the definition. Okay. So next definition. So if A is a square matrix, then the trace of A is defined by TR of A equals a summation I equals 1 to N of AII. What's the easy way of saying that in words? Because some people get like fear just by looking at the summation sign.
The sum of all the diagonal in the matrix.
And that's all this is. So the trace of A is the sum of the diagonals. Add up the diagonals entries, ignore all of the rest of the entries, and that's the trace. Any questions on the definition of the trace? Easy enough?
I have a comment. It's surprisingly simple.
Nothing wrong with simple, right? Nothing wrong with simple. Yeah, it is surprisingly simple, but there's some really nice things about the trace, as we'll see as we go. A lot of times you say, well, when you do stuff to a matrix, what have you done to the trace? Have you left it the same? Have you changed it, et cetera, et cetera? Does that make sense? So let's look at properties of the trace. So I'm going to go to the next page on this. I think I need to do. There we go. And these properties are hopefully obvious, at least the first two. So the first one is the trace of A plus B equals the trace of A plus the trace of B. Why is that obvious? I'm hoping you agree so I don't have to prove it, because I could prove it, but it's just busy work.
Yes, because the properties of summation.
What's that?
Because the properties of summation.
Yeah, summation of matrices, right? Is what you mean?
Yeah.
Yeah, so when you add two matrices, you just add the elements, right? Well, guess what? The elements along the diagonal get added. So if you add all of those, well, you're just adding. Do you agree that property 1 is obvious? How about property 2? Is that obvious also?
Yeah.
That should be obvious. If you multiply all the entries of the matrix, you're multiplying all the diagonals of the matrix. Well, if you're multiplying all the diagonals and you add up the diagonals, you can factor that k out. That's all that is. So is it okay if I just say it instead of write out the full proof? Because it's pretty simple. Just takes a while to type the summation symbol. That's the hardest part. Okay, number 3 may not be as obvious until you think about it. Any suggestions on number 3 is obvious? Because by looking at it, it may not be, because remember, AB and BA are not the same matrix. Do you agree? Right? You can't switch A and B and just say, I got the same thing. You get different stuff. But the trace is the same when you switch the multiplication from AB to BA. But why is that clear if you think about it?
Because it doesn't matter if you're reading by rows or columns, the diagonals will be in the same position in terms of multiplying.
Okay, how come?
Well, because they have the same like row and column number. So like, okay, the difference between like the order and multiplying matrices is that you take the first one's row and multiply it by the second one's column.
Except
But
multiply by is the wrong word.
well, dot product, sorry.
You take the dot product, and that's the key, is that you're taking the dot product of the ith row and the jth column. Well, if you switch that, well, it's still the ith row and the jth column, right? If you're just looking at the diagonal, so it's a dot product, and that's the key. So number 3 is obvious also as long as you think about it. It sounds like you were thinking about it, but never use the word multiplication for dot product, because that gets you in trouble with vectors. So the idea is that we're just talking the diagonals. Diagonals are the ith row, ith column. And if I switch the word column and row, then I say ith column dotted with the ith row. And the idea is it's true because dot products are commutative. So u dot v is v dot u. And it comes right from there. Any questions on these properties of the trace? Any questions? Okay, so if there's no questions, there's another property that's going to come up that's much more important than any of these. These are just fun, little easy properties. So might as well put them down because there's nothing to do. Do you agree? So now let's go to properties of similarity. So let's suppose A is similar to B. Then determinant of A equals the determinant of B. Why must that be true? I think I'll prove that one because it's worth it. I think it's easier to start with a determinant of B. Well, by definition, the determinant of B is the determinant of P inverse A P. Any questions on that? But then there's a very nice theorem about determinants and multiplication. What does that theorem say? Do you remember?
Isn't it the determinant of A times the determinant of B equals the determinant of A times B?
Yeah, and I could do it with 3 matrices instead of 2, and it still works. So it's the determinant of P inverse times the determinant of A times the determinant of P. And the good news is, as soon as you hit determinant, we're not talking about matrices anymore. Now we're talking about numbers, because the determinant of a matrix is a number. It's not a matrix. And we had another theorem. What was the theorem about determinant of P inverse? Do you remember?
Same as determinant of P.
Actually, it's not the same as determinant of P. That'd be a problem. Then actually this theorem be false.
Is the inverse of the determinant of P?
Yeah. Inverse I like to use, but remember these are numbers. So
Negative
reciprocal is the right word.
Or just reciprocal? Okay.
Yeah, it's a reciprocal. Well, guess what? Well, if you take the reciprocal of a number times the number, you just get 1 and it's gone. And since we're talking about numbers, you can switch the order now. So it's just determinant of A. Any questions on that? Isn't that beautiful? Okay, why are the rank of A and the rank of B the same? And that
It
comes from
wouldn't
a
even
theorem.
make sense to call them similar if they weren't the same dimension.
Well, similar just means that A is equal, that B is equal to P inverse AP. That's all it means. You can't just say proof because it wouldn't make sense. There's a reason, and it had to do with a theorem we had. Do you remember the theorem? Okay, so if you don't remember, let me remind you. And that is if you start out with a matrix and you multiply that matrix, and we're talking square matrices, by the way, and you multiply that matrix by an invertible matrix, you don't change the rank. Do you remember that? That was a theorem we had, that the rank is not changed by multiplying by invertible matrix. And the reason for that is if you have an invertible matrix, it can always be written as a product of the matrices of the elementary row operations. And remember that applying an elementary row operation doesn't change the rank. So that's the whole proof right there. Did I lose anyone? Any questions on that? Okay, how about number 3? Why is number 3 immediate?
We just proved it.
We just proved basically it. The trace of A equals the trace of B, because in the trace of AB equals the trace of BA, right? So let's do this one because it's so beautiful and easy to type. So the trace, actually, let's do it this way. So we're basically taking this, except changing from determinant to trace. And the idea is, what the big theorem says is you can switch the order of multiplication with the trace. Well, that's the trace of P inverse PA. We're allowed to do that with trace. Do you remember that? That was the property of trace. What's P inverse P?
I.
So that's trace of IA. What's the trace? What's IA?
Trace of A.
And we're done. There's the proof. It's a pretty little proof, isn't it? Any questions? Any questions on 1, 2, and 3? All right. So number 4 is A and B have the same characteristic polynomial. That one takes a little work to prove. But it's not hard. But my guess, maybe I'm wrong, is that if I asked you to prove this and I gave you 5 minutes, do you think any of you could do it? What do you think? You could say, no, I can't, or yes, I can.
No.
Okay, my guess is no one would be able to do it. Maybe I'm wrong, though. Okay, but what we can do is we can just use the definition and see what happens. So the definition is, let's look at the characteristic polynomial of B and see if we get the same thing as the characteristic polynomial of A. So we're going to take the determinant of B. Now B is P inverse AP minus lambda I. Any questions on that so far? And what we're trying to do is get rid of the P's and P inverses so that we can just have our A instead of our B. So here's the trick that you may not think to do, but it's what's going to work. So I'm going to copy and paste that in, and I'm going to adjust. Well, I can rewrite I as P inverse IP. What just happened? Do you agree that I'm allowed to do that? That P inverse IP is the same thing as I? That if you multiply those matrices, you get I?
Yes.
That's clear? Okay, now the reason I did that is now I can factor. I can factor on the left a P inverse and on the right a P. So now I could say this is determinant of, well, I can write this as P inverse times A minus lambda I times P. Does everyone understand what I just did? That you're allowed to factor on the left and right? That's called the associativity property of matrices. And that was one of our properties a long time ago, early January. Okay, so now that we have that, well, now I can use the big rule that says that I can break up multiplication with determinants. And I can write that as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. But we already had earlier the determinant of P inverse times the determinant of something times the determinant of P is just the determinant of that something matrix. So this is equal to the determinant of A minus lambda I. And that's the proof. Any questions on that? And the determinant of A minus lambda I is the characteristic polynomial of A. That's the definition. Anyone lost on this? Okay, why is number 5 immediately after getting number 4?
Because they have the same eigen, the same characteristic polynomial.
Right, they have the same characteristic polynomial, and the eigenvalues are the roots of the characteristic polynomial. Well, if they're the same characteristic polynomial, then they're going to have the same characteristic polynomial as roots. So there's nothing to say on number 5. Number 4 is all the work. Any questions on this theorem? Okay, so it's a big theorem, and we'll use it from time to time. Okay, now comes the big definition of the day. So this one you want to definitely, get this down. And I love the word. It just, I don't know. If you ever had one of those words, it just does like wonderful things to your soul. This one, I just saying it. A is diagonalizable. Feels so good, doesn't it? So A is diagonalizable if A is similar to a diagonal matrix. So that means that there exists a diagonal matrix D. So now we usually use D instead of B because the word diagonal has the first letter D. So that way you remember what you're doing, such that A is equal to P inverse dP. Any questions on this big definition? Any questions? Why is this important?
Well, if a matrix is diagonal, then it's a lot easier to take the determinant of it. Not that much.
And anything else. First thing, diagonal matrices are so much easier than non-diagonal matrices. Do you realize? Not just determinant, but inverse if it's invertible. You could take the inverse of a diagonal matrix if, as long as there's no zero, as long as it's invertible, probably in your sleep, right? With your eyes closed, right? You just take the reciprocal of each of the diagonal elements, and that's it. That's your inverse. Diagonal matrices are beautiful because you can do stuff with it. Let me do one just to show you, and this is going to come out later this week, but I want to do one just for fun. What if we have the following? Takes a bit to type, but it's worth it because it's so important. I want to go bracket. I always have to do it the right order. Just a minute. I think I need it this way. Hopefully I got it right. I want you to do this. What do you get? I want you to do this multiplication. So it's xy 2003 times xy. And I'll even put an equal 1 just for fun. Tell me what you get. Put it in the chat box when you've got it. This shouldn't take long. This isn't some really hard linear algebra thing. This is matrix multiplication. It's just simple ones. And you'll get an equation. So let me know what you get when you're done. It's much simpler than that. The hint is there's no vectors when you're done. No comma. No comma. There we go. Jesus got it. 2x squared plus 3y squared equals 1. Do you need me to work that out? You need me to work out how do you do matrix multiplication? Maybe I should, because I saw other answers, and that means that you need some more help on this. Okay, so first thing I'm going to do the 2003 by xy. And when you do that, what you get, let's see if it lets me do this. There we go. So if you take 20.xy, you get 2x. There we go. If you take 03.xy, you get 3y. So now I multiply these two matrices. Notice this is a 1 by 2 times a 2 by 1 gives you a 1 by 1. And a 1 by 1 is just a number, you know, with variables in it. So that's going to be, when you're done, 2x squared plus 3y squared equals 1. In a word, what is that? One word?
Ellipse.
An ellipse. Okay, so that's an ellipse. Do y'all agree? I'm going to just slightly change it. What if we had, instead of 2, 0, 0, 3, what if we had 2, 1, 1, 3? Didn't change much, did I? I want you to work that out. Tell me what you get. Good, good. So you get 2x squared plus 2xy plus 3y squared equals 1. I lost a plus. Do you know what that looks like? And the answer is you probably don't. Am I right? Would you know how to graph that? If I told you, you know, sit there, pencil and paper, and graph that. How would you graph this? Any thoughts?
I don't think
Take
3D
the
top plotter.
I couldn't really hear you.
I was going to say take a derivative with respect to a certain variable and set it equal to 0 if you can.
Okay, that could give you max and mins, but doesn't give you the whole shape of the thing, right?
No, but that's a start.
As a start, I'd probably do a t-table and hope to get something that I could like get enough dots that I can like put it out. Actually, I shouldn't say I would do it, but if I didn't know linear algebra, that's what I'd do. Does that make sense? On the other hand, if we can diagonalize the matrix and make this matrix diagonal, then I'm either going to get an ellipse or a hyperbola, possibly a parabola. I'll get something like that instead. And then it's easy to graph. So one of the big reasons why you want to be diagonalize a matrix is what it does is it gives you a different basis at which you can draw the picture and see what you get. Any questions on that? Okay, and that's a big deal because you want to make sure it's as easy as possible. Okay, so now let's move on to a big, huge theorem that tells you how do you diagonalize a matrix. So if it is diagonalized, how do you actually find that diagonalization? And here's the big theorem. So let A be diagonalizable, then P is the matrix of eigenvectors, and D is the matrix of eigenvalues, sorry. This diagonalizes A. So that's a big deal. So what it tells us is that if we have some weird conic like this, and we want to write it and figure out what the thing is, then what we can do is we can diagonalize the matrix by finding the eigenvectors and the eigenvalues And then we have our P, we have our D, and we know what to do. Any questions on that idea? Okay, and just a note, you can always take an eigenvector and divide by a constant and it's still an eigenvector. So you can always let that eigenvector be a unit vector if you wanted to, which means that what you can almost always do is you can write P in, if it's 2 dimensions, as a rotation. And that's a nice thing to be able to do. So you can trust me on that, that does work. Any questions on the theorem? Okay, now corollary. Sorry, theorem again, before corollary. That is, if S is the collection of eigenvectors corresponding to distinct eigenvalues, lambda 1 through lambda k, then S is a linearly independent set. Any questions on this theorem? Okay. And then finally, and this is a biggie, if A has n distinct eigenvalues, then A is diagonalizable. Because if you can find n distinct eigenvalues, that means that there are n linearly independent eigenvectors. And that means that if you look at the matrix whose columns are those vectors, then that matrix must be an invertible matrix. Because you need it to be invertible. If it's not invertible, then you don't get a P inverse. Any questions on this in this big corollary? We'll do examples, and I think then things will hammer in. I want to hammer in again. If A is diagonalizable, then you can just let P be the eigenvectors and D be the eigenvalues. And that diagonalizes A. Okay. Why is that true? Any ideas? Any thoughts? Okay, so I think it's easier to copy and paste this guy. All right, so we can say A is P inverse DP. All right, well, what I can do now is I can just multiply. If you look at this, if what we can do is we can multiply by what? Any ideas?
By P?
Hmm?
By P?
I can multiply by P. And in fact, I think I might have this backwards, actually. That's right. I'm going to go like this and go P, D, P inverse. So I can write that AP equals P, D. Is that clear? Just by right multiplying by P. Okay, but what's AP? Any ideas? And the key is understanding that P is a matrix of eigenvectors. And the way you multiply is you take the column And you take A times the first column, and then A times the second column, and then A times the third column. But A times the first column is A times the first eigenvector. Well, guess what? A times the first eigenvector is just the eigenvalue times that eigenvector. Do you agree? Because that's what the definition of an eigenvector. So that means that we can write down, I'll just say it, that the first one gives you A times the first eigenvector is the first eigenvalue times the first eigenvector. But PD is the same idea because D is a diagonal matrix of eigenvalues. And if you want that first column, then you're only looking at the first eigenvalue times the first column of P. And that gives you the same thing and you're done. That's the whole proof. Anyone, any idea? Anyone lost on what I just said? So this always works. And that's the big deal. Okay, and it always works as long as it works. And that means that you want to have n distinct eigenvalues. Okay, if you have n distinct eigenvalues, it always works because then you get a p. Otherwise, you don't get a p necessarily. All right, I think I want to do an example. And maybe we'll do a 2 by 2 matrix just to make life a little easier. So let's suppose we have A equals, we need a matrix out of this. And let's say it is, I didn't come up with one ahead of time. I should have. That was my mistake. How about 1? Let's see. How about 1, 1, 1, 2? It's probably not going to be that pretty, but it should not. Let's not make it 2. Yeah, I can make that 2, but let's make this 1 a 6. That should work. If I did my math right in my head. You're going to get not ugly square roots and stuff, but that's okay. All right, well, how do we find the eigenvalues and eigenvectors?
Determinant of A minus lambda I.
Yeah, you could do that, and that will work. That will work, but there's an easier way.
You gave us a formula for a 2 by 2.
Yep. So we know that the characteristic polynomial is the following, and I need to make it a math symbol thing. So we're going to have lambda squared, and then minus the trace of lambda. The trace is 3. Are y'all good with that? So 3 times lambda. And then plus the determinant of lambda. And the determinant is 2 minus 6. Y'all good with that? So that's minus 4. Any questions on that? So again, you could do it the long way, but this is a lot easier. So it's always the lambda squared minus the trace of lambda plus the determinant. If I did everything right in my head, unless it's backwards on the plus and minus, I got to remember that. Okay, so what do you get?
Lambda equals -1 and lambda equals 4.
Yep. So lambda equals -1. If I did everything right, then we get lambda equals -1, comma, just 4. Sorry, it's equal to 1, comma, -4, right? Is that right? Let's see. Lambda minus, so it's negative, let's see, it's lambda minus 4. So it's -1, comma, 4, right? Any questions on that? Okay, so if I did everything right, then that does work. Let me double check. It's 2, 6, 1. Is that right? Subtract 1, that's a 0. 6. No, I think I have it backwards, don't I? So we have 1 minus lambda, 2 minus lambda. So it's lambda squared. 1 minus lambda, 2 minus lambda. Does that look right? What do you guys think? I may have to, huh?
About right.
Let me double check. That we got the right thing going on. All right, so we have that for sure. And that gives you the constant should be 2 minus 6 is -4. Yeah, that looks good. Okay. So we now got that. Now we need to get the eigenvectors, right? How do we get the eigenvectors?
Substitute our eigenvalues in for lambda. And then
Right. Right. So that's even if you're using this formula that I use, it's still good to write down the minus lambda because we got to plug it in. So 1 minus -1 is 2. And 2 minus -1 is 3. Yeah, this does work good. So, and those are always going to give you 0 on the bottom when you RRF. And I can take that 2, make it a 1 and a 3. I'm RRFing here. So that gives me the vector, the eigenvector. Let's make a vector out of it. So if we let the free variable be 1, then the x value is -3. Any questions on that? Okay. And now I need to get the next one. Maybe I should write down this is lambda equals -1 or say v sub -1. Now let's do the same thing and copy and paste and then change. And do v sub 4. And if you subtract 4, 1 minus 4 is -3. And 6. And then what we get is the following. Well, if you can change that to, instead of a -3, 6, you can make it a 1, -2. And that gives me 2, 1. If I did everything right, does that look right? So we subtracted 4, 1 minus 4 is, no, I think I made a mistake there. So it's 1 minus 4 is -3, -3, 6. Let's do it again. -3, 6. And then we're dividing it by 3. Let's see if that works. Yeah, that should work. And 2, 1, I think. 1, 2. Yeah. Any questions on that? Okay, what does that give us? Oh yeah, this works. This works. So what do we now have? What's our P?
-3 1 comma -3 1 and 2 1.
Yeah. So you just take P, and it's going to copy and paste. It's easier to type that way. Change that A to a P. And then our matrix is a -3 1 as the first column, and 2 1 as the second.
Does it matter which vectors we make columns?
No and yes. Don't you hate that, Lancer?
Yeah.
Okay, so it doesn't matter which ones you make columns, but you need to be consistent with your lambda. So at this point, it doesn't matter, but now we need our D. Oops. So now we need to get our D. And this is where it matters. That's why it's a no and yes answer. So notice that the -3 1, that corresponded to -1 as the eigenvalue. So that means -1 needs to be the first one in the diagonal, and the second one in the diagonal needs to be a 4. And that's a 0, and that's a 0. So you could, if you switch the columns in P, you also have to switch the diagonal elements in D. Does that make sense?
Yeah, thank you.
So it doesn't matter. You can go either way, but once you've chosen P, then you have to choose D correctly. So you can't just randomly do it and then forget about it. You have to keep remembering. Okay, so that tells us we've now diagonalized our matrix A, because we have our P, we have our D, and hopefully you know how to find P inverse if you need to, right? 1 over the determinant times the adjoint of P will give you P inverse. And then that gives you your P inverse dP. Any questions at all on this big theorem in this example? How to get D? Okay, so notice lambda equals -1 and 4 are 2 eigenvalues. So D stands for diagonal. So I write down the diagonal matrix that has the eigenvalues. Does that make sense, Ralph? Yeah, very important to ask questions when you have them. This is a very, very important piece of linear algebra in the how to do it. So it's not all that like theoretical proof stuff, but it's very important in applications. Because there's sometimes you look at this and you say, okay, all I really care about is D. That happens a lot because D will tell you what's going on. Okay, in the real world I'm talking about. And so all you need to know is your eigenvalues, and then you know what your D is. So for example, a physics example is that in the matrix that defines relativity, you need to have 3 positive eigenvalues and 1 negative eigenvalue. Okay, and you trust me on that, and that gives you your relativistic space. And then if you go into a black hole, by the way, you switch everything. no one really understands what's going on. They know the math, but no one understands what it means to switch time and space. But you have to if you go into a black hole. So when you go into a black hole and come out, tell me what happened. But I'll let you know that it's all about the eigenvalues and eigenvectors. Just trust me on that one. Okay, but these come up all the time. In artificial intelligence, the largest eigenvalue tells you the most important combination of your variables that you want to look at and use. Okay, and the eigenvector corresponding to that eigenvalue is the combination of your variables that you're looking at when you're doing AI. And so you turn everything into like combinations of different stuff, because the combinations of the variable are what matter, not just individual variables. So again, it's all high level, so it's hard to explain to all of you, but you're going to get there, just not at LTCC. You'll get there when you go into your bachelor's degree. Okay. And similarly, if you're doing electrical engineering, the eigenvalues and eigenvectors tell you how the correspondence is with your circuit that you're dealing with when you're doing a circuit analysis. All right, so now some more stuff, more theory. I want to do at least one good example. Okay, so here's a big definition, and I call it a definition / theorem. The book calls it a definition, but really it's a theorem too, and you'll see why in a bit. The eigenspace, maybe I'll write down in red, because that's what we're defining. The eigenspace that corresponds to the eigenvalue lambda is a set of all eigenvectors corresponding to lambda. Okay, so for example, in this example I just did, I found -3, 1 for this first eigenvector. Is that the only eigenvector that corresponds to -1? What do you think?
No.
Can you give me another one?
Negative 6, 2.
Yeah, -6, 2. You can multiply by any constant and you'll get an eigenvector. Do you see that? And I should write, this is a subspace of Rn. I need to add one more thing. If we adjoin the zero vector. Because in the definition of eigenvector, you're not allowed to have 0. Remember that? So if you do adjoin the zero vector to the set of all eigenvectors with that eigenvalue, then you get a subspace. And remember, a subspace means that if you have any 2 of them and you add them, you get another one. And if you have one and you multiply by constant, you get another one. And you also have to have 0. So that's what I better put in 0. So this is a definition / theorem. It's a definition because we defined what eigenspace is. And then it's a theorem because we're saying it is actually a subspace. Any questions? Now, it may seem obvious after looking this example, like, of course it's a vector space because I got this vector, I can multiply any constant, you still have a vector, and that's it, right? Okay, but this example, we had a one-dimensional null space for this matrix when you subtracted the lambda I. There are examples where you get a 2-dimensional space or a 3-dimensional space. So if you get a higher dimensional eigenspace, then there's more work to do than just saying, well, if you multiply by constant, of course it's true because that's how we've done it.
Does it contain the 0 vector too?
Well, it does because I wrote this. So it's a subspace if we adjoin the 0 vector. Do you see?
What does that mean exactly, to adjoin the 0 vector?
So
Just
what
say
it is
there.
that, so if you just look at the eigenvalues and that's it, then it's the line through the origin without the 0 vector, without 0. Which is frustrating because you don't want a line with a hole in it, right? So it means fill the hole up.
Okay, that makes sense.
That's all it means. Just fill the hole up, put the 0 vector in, and we'll call that the eigenspace. That way we can actually say it's a subspace. Otherwise, you can't say it's a subspace. Okay, so here comes a big theorem. And A is diagonalizable if and only if the dimension of the eigenspace for each eigenvalue lambda is equal to its multiplicity. Why is that true?
Multiplicity, what's that mean again?
Okay, so remember that when you found an eigenvalue, you found the determinant of A minus lambda I, right? You found the characteristic polynomial, and you found the root of that polynomial. Do you remember that? So the multiplicity of a root is if you can factor the polynomial as A minus, as the root minus, as X minus the root or lambda minus the root. If that has a square when you factor it, then it has multiplicity too. So do you remember how that works in algebra? In intermediate algebra, is the multiplicity is the power of the root? Do you remember doing that way back in your life sometime? Not this year, years ago. So for example, let me give you an example. Whoa, I don't know what just happened. Let's try this again. Let me just give you an example. Let's suppose we had the following, and let's suppose I factored it, and I said this was lambda minus 2 cubed times, oops, there we go, times lambda plus 3 to the 5th power times, how about lambda minus 7? Let's say that was a characteristic polynomial after you factored it. What's the multiplicity of the eigenvalue -3? Can you tell me?
5.
5. So what that says is if you take A minus A plus 3i, and you write that matrix down, then that matrix must have a kernel of dimension 5 for this to work. Does that make sense? Because remember that we found the kernel to find the eigenvectors. Do you remember doing that? Like right up here? That's what we did. We RREF'd it, found the kernel, and in this case, we only got 1. We got dimension 1, so we just had 1 vector to write down. But sometimes you get more than 1 dimension if you do that. And if the characteristic polynomial is what I have here, and you do A plus 3i, then if you look at the null space of that matrix, it must have dimension 5, okay? Or if it doesn't, it's not diagonalizable. Do you see that? Now, I don't have enough time to prove this theorem, but it's an important theorem to remember. I won't make you prove it. But the proof basically is that if the dimension's right, then you could just write down all those columns, and guess what? Your dimension's right. So that means the rank must be n when you add them all up. That's all that is. That's the full proof. But I don't have time to write it all out. Any questions on this? All right, now the last bit. I want to spend the last time on complex numbers. Okay, so if lambda is a complex eigenvalue of A with eigenvector V, okay, and V will be complex also, by the way, then the complex conjugate of lambda is an eigenvalue of A with eigenvector that is the complex conjugate of V. And recall that the complex conjugate of A plus BI is A minus BI. Okay, I think I'd rather do an example than a proof. Don't you agree? I mean, I could prove this for you, but I think you need to see an example to see what's going on. Any questions so far? All right, so let's suppose we have the following. A equals, I'll just do a 2 by 2 because we only have 4 minutes. And let's see, now I need the -3. Actually, trace plus determinant. I think that one will work. Okay, so let's suppose that's our A. How do we find the eigenvalues?
The determinant of A
Use the
minus
2 by 2 formula.
Yeah, you determine A minus lambda I, and then you find it. And remember, we had a formula, and that said that lambda squared. And then we had minus the trace, so that's minus 4 lambda. And then we had plus the determinant. The determinant is 11. Set it equal to 0. All right. Can you do that? By the way, this doesn't factor nicely. But what do you notice about b squared minus 4ac?
You're going to get a negative in the square root.
Yeah. So let's actually do it because it's worth it. So what we get here I think I need to make an equation. There we go. So we get here is lambda is equal to fraction probably been a little while since you had to do the quadratic formula, but it's negative b, which is 4 plus or minus. I'm gonna write, I think this will work. Let's see, did it? Yeah, plus or minus the square root of b squared minus 4ac. So b squared is 16. So it's 16 minus 44. 36. So that's what, negative 28, if I did it right. Sound right?
Yeah.
So it's negative b plus or minus square root of b squared minus 4ac all over 2a. It's all over 2. Any questions so far? Which is equal to. So I could do 4 over 2 is 2. And then we're going to have plus or minus. And now we're going to have the square root of negative 28. Well, the square root of negative 28 is the square root of negative 7 times 4. I can take that 4, pull it out, get a 2, cancel the 2's. So plus or minus I, or let's go root. There we go. Square root of 7 I. Any questions on that? Okay, so the first thing is the fact that if lambda is an eigenvalue, then its complex conjugate must be an eigenvalue. That's immediate because we're talking about, there's a theorem from algebra that if a minus bi is a root of a polynomial, then a plus bi is a root also. Do y'all remember that? I hope. Okay, but then what do? Now we need to find the eigenvalue. How do we find the eigenvector? How do we find the eigenvectors?
Plug that in to a minus lambda I.
Yeah. So I'm going to take the -1, and this is particularly important. You're going to go -2, and then a minus root 7i. Or I'll make it plus. I could choose either one, right? Plus root 7i. And then -2. And why can I write 0, 0? Why can I do that? Anyone know? You're not telling me? You can, because we're finding an eigenvector. When you're finding an eigenvector, we always know the rank can't be 2, which means that the bottom must be all zeros when you RREF. Okay, I could take that 1 minus 2 and make that a -1. And then I can get my vector by setting the free variable to be 1. And if I set the free variable to 1, then what do I get for the vector? Something comma 1. It's kind of messy, but that's okay. You get -2 over -1 plus root 7i. Kind of messy. Comma 1. Okay, or easier if you want, instead of setting equal 1, let's set it equal to -root plus 7i. And then we get that. Okay, and there's my eigenvalue, or eigenvector corresponding to 2 minus root 7i. How do I get the eigenvector corresponding to 2 plus root 7i?
Same way.
I don't have to do anything. The hint is I don't need to do it the same way. All I do is take the conjugate of this vector. So where I see a plus root 7i, I make it a minus root 7i, I'm done. That's it. And I'm out of time, so I need to be done. But I think I'm going to stop the recording. I went a little over, sorry about that.